independent source and dependent source. So what's the difference?
This main.
The independent source is the general source, right? And in the general source we have independent voltage source and independent current source. But the dependent source generally is controlled by one signal in power circuit.
Yeah.
So the signal might be current or voltage. What is it? Can it be voltage? Can it be voltage? So does the dependent source controlled by current and voltage together?
Yeah, CC is CS, BS, voltage control, voltage source.
Yeah,
voltage
I mean,
control.
can they control it at the same time?
Together, this current and voltage.
Yes. Okay.
Yeah.
Right. So we have dependent voltage source and dependent current source. Here, this one is the dependent voltage source in the purple, right? The most general one, we have a circle and sign inside. And the left-hand side is the sign which is in this book.
Yes.
In some Chinese book, we use this for simplification.
Yeah.
Okay, second one is independent current source.
Okay,
We use this one. We use the arrow, we put it inside the circle to stand for the real direction of the current source. Okay, then we have the dependent source, and we see for dependent source, we just change the circle to a diamond.
Yes.
So, for a voltage or current controlled voltage source, it's like this. The figure inside a diamond is positive and minus sign. Okay, so this one means it's a voltage source. But what controls it? It's the side from here.
Yeah.
Okay, if it's V, it's voltage control. If it's I,
It's current control.
it's current control. So, similarly, we have a current or voltage control current source as well. So, inside the diamond, we have arrow to stand for a current source, right? Here is the four typical dependent source of our source. So, I just want to know what is a dependent source in power line. So, have you ever seen it?
Everywhere.
In power line. So, what happens at the appliance in the control?
It's dependent source. This one is dependent source.
Actually, inside everything we might have dependent source because amplifier, sometimes amplifier is dependent source. So in most of the circuits we have amplifier. So most of the circuits is a circuit with dependent source. Understand? Because the amplifier is a typical dependent source. So that is why the dependent source is important for us, important for study. But we don't like to see it in our examination or test, right? If we have it, the calculation becomes more complicated.
Yeah,
So
this
we
is
don't
two
like
case.
it. But we need to remember the things, if it looks more difficult, is more useful. Okay. Okay, let us have a look at this example. The source on the right hand side is controlled by the current passing through MC. Okay, because the current goes through C is this I, right? And the diamond means it's a control source. Okay, so the voltage here is 10I. So here is some applications of dependent source. The first one is transistors. Okay, here. Okay, that is what I talked about. And this one, amplifier, operation, amplifiers. Okay, now we're going to see the ideal circuit element. So what is the definition of ideal? What does ideal mean? What does ideal mean in our book?
This meaning is
We have many circuit elements in practical life.
Yes.
We produce maybe a real resistor or real battery. Okay, they are circuit elements.
The real.
Is does they idea elements? Are they idea elements?
Idea.
Battery is
Idea.
idea? No,
Wait.
it's not idea. Idea means no resistance.
Oh.
Understand?
But better have a resistance.
Battery, the real battery, they must have resistance, right? So, in our life, example,
Turn on. Activity is on.
okay, more like, this one is the battery, right?
Yes.
So, this one is the practical element. But what is it? Circuit element. So, in our circuit analysis, what is the motor of it? We know it must have a voltage source inside, right? And we say, does it have resistance? Does it have resistance?
Yes, you will have resistance.
So we must have a resistance inside as well. So this one, we say, this one is the ideal resistor. The ideal resistor just focus on the resistance. The ability to resistance what? Current. Or resistance
What?
resistance current.
Yes.
Okay. So this one is the ideal one, just focus on R. And this one is the ideal one, just focus on the voltage. This one, no resistance. Okay. And we also have this one and this one. We say all the elements are ideal elements in the circuit analysis. Since the circuit analysis is just for ideal circuit element. It's not for the real one. For the real one, we need to do one more thing. What is it?
Because this is the better inside have a resistance.
We need to do one more thing. Our circuit analysis is just for ideal elements, not for this. So, from this one to this one, we need to make a real ideal model of it. Understand? This one is circuit model. This one is real elements. So, are they equivalent? Are they equivalent? Are they equivalent?
No.
No. Why?
This battery have a small resistance.
They are equivalent in some special situation. That means for one element, it might have different circuit model. If we change the situation, the model might be changed. Understand? If we change the temperature, model change. If we change the pressure, model change as well. So the circuit model is the model for the real one in some special situation. And circuit model is comprised of ideal current source or ideal current element. This element is just reflect one main property. Maybe for resistor, it just reflects the resistance, right? And for this one, inductance, it reflects inductance. The capacitor reflects capacitance. It just reflects one thing. But in our real life, our element, it doesn't just has one property, right? It might has R, maybe has inductance together, right? Most of the case, for example, the bulb, it has R, right? And it might have this one as well. Understand? So for real elements, and if we put it inside the circuit model, it becomes like this, or like this. Here I show an example. This one is a winding resistance in our real life practice.
Variable resistance.
If omega is low, the main electron magnetic phenomenon is resistance. That means when omega is low, it is this one, right? But if omega is raising up, the capacitance and inductance cannot be ignored. Then the resistor becomes this one. So that is what I talked before. So for one thing, okay, this one is the real one, right? But different case, it has different circuit model. Understand? So model is an ideal model for some special case. So we need to understand this. Okay, now we're going to have a look at the ideal source. Here is ideal source. We have two types. One is ideal voltage source, another is ideal current source, right? Okay, source is simple, and the reference direction is active sign convention. Satisfy active sign convention we talked before. And here, what is our marks? Here, you can see here, this one is a voltage source, and for constancy, we have V equal to I, R, okay? If this one equal to C, if the V is a constant, and if we connected these 2 points, what will happen? If we connect these 2 points, if we short it. Short means here is no resistance inside, right?
Yeah.
Means our R tends to 0. When it tends to 0, from this equation, we can see C is a constant, and this one, if it tends to 0, our I must tend to infinity. When I tends to infinity, what will happen? What will happen when I tends to infinity? You know, what is current? For instance, the current, I give you current. The temperature arises, right? Okay. It rises from maybe 0 to 10 to 100 to 1,000, and what will happen?
Burn.
So burning. So it's forbidden. The voltage source cannot be short. Okay. If you don't understand, or if you forget this one, we can just use this equation, right? This equation is Ohm's law, right? And we just make a short derivation, and we can derive. Because the voltage source cannot be shorted, and the current source cannot be opened. This one, sometimes we derive useful, right, and mistake them. But if we have this equation, we can derive very quickly. So it's not a problem for us as well. Okay. Here we have this one, the ideal current source. For ideal current source, still is one equation. What is it? What is this equation? I just told. What is this equation? What's the name of this equation? What's the name of this law? What's the name of this law?
Ohm's law.
Oh, good. Ohm's law. Okay. Okay, from Ohm's law, we reform it like this. I equal to V over R, and we make it to a constant because we just think it's a DC constant current source, okay? And then, if we close this switch, what will happen? No, if we open this, open it, R cancel.
Infinity.
When R tends to infinity, we see the R is in the denominator, right? In the denominator means
Infinity.
right hand side of constant, denominator infinity. That means if we want the right hand side still a constant. We have to make b tends to
infinity.
infinity. So very, very, very large infinity will bring what? Very large infinity. Or
Of
very
voltage.
large voltage difference will bring what?
Fire.
Bring the spark. Understand? If we have raining, right?
Spark.
That means raining. Okay,
No.
we'll find the air, when the air is, I don't know how to say it in English. In Chinese it's the 击穿, like this, to break. If the voltage is very high, if the potential difference is very high, we say the material will be broke, and it will be broke, broke.
Yeah, I saw some cases.
Yes. For example, we have a wire, okay, and we have some skin. We have some skin on the top of the wire. Okay. So if the voltage is very large, and the skin will be broken. So when the voltage difference is very large as well, the air will be broken and there will be a flash. Understand? There will be a flash. 闪电.
Oh.
Okay.
Lightning.
Okay, lightning.
Lightning.
There will be a lightning. That means when the potential difference is quite large, the air will be broken and there will be lightning. Okay. So that means it's not good. Okay. When the air is broken, when it has lighting, when it has spark, what will happen? It will be a fire as well. So it is forbidden as well. It's not good. So we just know for voltage source we cannot short connect it. For a current source we cannot open it. Otherwise there will be a safety problem. There will be fire. Okay. Long parallel circuit. Actually this one is a very typical definition. Have you ever seen it before? Long parallel circuit. It's just maybe description of a circuit which has a very, very special size. The circuit size B is smaller than the wavelength lambda. Just show you an example. I know it's quite mathematics. I just show you an example. Do you know?
6 gigameter.
6 gigameter?
This lambda, wavelength.
Yeah, yes.
6 gigameter.
Right?
Yes, sir.
You can calculate it, right?
Yes. This
You can see I put the equation here, and after calculation we find for our power system, is working at 60 Hertz. In China it's 60 Hertz. How about your country?
60.
60 as well?
50. Oh, my country is 50.
In Chinese
It is also 50.
Okay, in Chinese 50. But in some other countries they can
60.
Okay, but in China it's also 50.
But this is the standard frequency is 50.
Okay. So, and we can calculate the wavelength. This is one. So if our size of our power system is smaller than, what is means greater smaller? Smaller.
Nanometer.
It means if 86 we say smaller than 1. The difference is 10 to the power of 3. So we say it's smaller. But in China, we have maybe a power system with very, very, very high pressure. Okay, so So the length is very, very high as well. Maybe we have a length of wire with the size of 600 kilometers. So between this one and this one, it's not smaller than, it's not greater smaller than this one, okay? 6, 10 to the power 3, and this one just 10. So we say this condition is not satisfied. So what does it mean? For a small circuit, what is small circuit? Like this one. Do we have smaller circuit in camera?
Yeah.
Yes, we have, right? Do we have small circuits in our mobile phone?
Also there.
Yes. In every electronics devices, we have a small circuit inside. And the size of the circuit is smaller than the wavelength lambda, smaller than this one. Okay. So we can use circuit analysis next step. But for our power system, I just show you. The length of the power system is 600 kilometers, right? So this condition is not satisfied anymore. So what should we use to analysis? See, I will say, you can see our circuit analysis is useful, but it has condition. The condition is circuit size D must be very, very small, okay? Smaller than the 6,000 kilometers, okay? If it's not satisfied, like this one, what should we use to analysis?
Ideal.
Circuit analysis? Can we use circuit analysis?
Ideal circuit element.
No, we can't use circuit analysis. Because circuit analysis must satisfy this condition. Must satisfy this condition. So for a large power system, we cannot use circuit analysis anymore. What do we use? What do we use?
Because this last part is system when we are going to be transmission, we have some loss. So that's how you can.
Yes, but if this condition doesn't satisfy, we cannot use. So what should we use? We say we use electric magnetic field analysis, because that is the basic thing for our electric and magnetic things. Okay. And in our circuit analysis, we have RLC, right? But for power system, we say sometimes we also have something like this. But in another cases, we didn't use this. We focus on the material. We focus on the material. We concentrate on material property like zeta epsilon,
That's good. Yeah.
zeta gamma,
Gamma.
zeta mu.
Beta.
It stands for another 3 property of our material. Okay, so it's not it's a little bit far away from our course. Just introduction.
This is the transmission of this.
Yes, I just want to tell you guys, our circuit analysis is maybe for small circuits. For very large one, we cannot use it. So we must know this, okay? Okay, here is some application and it is on the page 17 of our book. And you can go back to have a look at this. And here we just show you some simple things. Okay. Okay, this one is the main content for the chapter 1.
The electricity cushion.
And to be honest, we might use maybe 2 days, to finish all the content. Go straight, and then we start the new content. And on the 6th week, and we have examinations, and our examination is very, very easy. Maybe we have 4
pass.
Yes. But if you want to get a very high score, you need to finish all of them.
He will finish.
You need to finish all of them. But our examination question is from our homework. Okay, from our homework. So when you finish your homework, and make sure you know how to solve it and know how to choose 4 from it. Understand? Is it easy? Easy? Okay, easy. But it's not an open book examination. It's a closed book examination. So you guys still need to make sure you know how to do everything.
What will happen to the other students who are not here?
Who is not
here? I mean, those who went back to
Actually,
Japan.
from my point, I want to give them custody. Just want to give them custody.
Okay.
So parents never pass.
Okay.
All of them passed.
Okay.
And people are pass.
So because you know, in maybe 10 years before, this situation happened once.
Yeah.
So in my university, some people go back home.
Yes.
It just maybe half of them stayed in the school, and another half go back home, including me.
That time they had a panic.
Yes. And my teacher, she didn't give us any examination. If you study good,
Is good.
it's also pass.
So you can be.
Because they didn't attend the examination, no? They
Yes.
didn't attend the examination. So when we have time difference, you know, when we do the examination at home, I can't make sure if we give them the result. Okay, so it's not unfair to you guys. You understand?
That is not your never is it?
So
Parikha na dilo
if
pa.
I'm your friend,
Yes.
I ask you, please give me the answer about homework. About homework.
Homework?
No. I can't give it to you. You do this?
Homework classes?
Homework.
Oh.
If I'm your friend, I'm asking you for your homework. Do you give it to me?
Sometimes we give, sometimes we don't.
Oh, are you sure? So you don't have a friend anymore.
I gave every time last year because I finished this homework fast and
Yes.
gave all of them.
But you have the examination in the class, okay? But they have the examination at home.
Yes.
Nobody monitor them. So they can call me.
They
Okay?
call me and we say,
They can call me. So it's not a fair thing. So if they didn't attend the course, I just need to give them pass.
just give the pass.
Yes, I just want to give them pass.
However, finish with the night. Don't go night from night.
Because I want 100% sure if I give them chance to have examination at home, they must pass. Right?
Yes. So
Nobody will fail.
go finish them. So the pass already. Finish them. Now we're pass with you na. अरे बोधा की विजय एक बार
Give us some suggestion.
कोई तो दिशा होमवर्क दिया तो
What?
कोई नहीं
Suggestion for exam.
What do you want? Suggestion for examination?
Yeah.
Finish your homework.
There are many questions left in our
Just
homework.
finish all of them. Finish all.
It's okay.
I know.
Do it.
I know you don't want to finish it, but you have to finish all of them. And
Mhm.
then maybe 4 questions, 1 question, 25 points. If you finish 2, pass. If you can finish 3,
It's good.
good. Finish 4, distinguish.
Who will finish first? Who will win?
You don't try your best to finish 4, right? Our examination is 2 hours. You have to finish 4
Question.
problems in 4 hours.
Sure.
Okay, with notebook.
Okay.
Yes.
Okay.
But can you tell us this? Who is this? I mean,
I just know it's in the week 6, but I don't know the exact date. Oh, 5. No, year 5, year 6. After your
16. That's right.
I think it might be Sunday. We
What
have
happened
one
now?
more closing on Monday. Yeah. Listen, I think it might be Sunday. It might be Friday as well. No, I think the timetable is not in the course.
I think so.
Examination is not in the course. So do you guys is the second year?
Third year.
The third year?
Yeah.
Oh my god.
Because last year this course was second year course. But
No,
we
this
didn't-
course
the first year.
for our students is the course for the first year.
Yeah.
It's the course for the first year. Okay, so what is the reason you didn't learn this?
The office gave us this subject in the second year.
My leader told me that they didn't find any person who can teach this. So,
Yeah, another teacher for this third semester. Not you. That time he saw that he had no time. He going to another country for maybe another
Okay.
degree. After that, actually.
okay.
That's why we missed this third semester course.
Okay.
About this one,
But
right?
ma'am, for the Chinese students, they choose their own subject and their own credit, which subject they want to take this semester, or after that they can choose them. But we can choose. The office will decide by us that which subject we have to study in this semester.
I know it's a problem, but you know they need to find the proper person.
Yes.
But I think you are the proper person for this course.
They need to find the proper teacher because I am not the teacher for this school. Okay, I'm the teacher for the electrical and information engineering school. So
We are also in the same department, but we are under the international college.
yeah, that's the truth.
This is the problem.
So you want to go back to our school?
I want to learn.
But if we go there, we have to study in Chinese.
This is the
Yeah, that's the reason.
That's the problem.
That's the problem. And you might not follow our process.
Yes.
It's really fast. Really fast.
Yeah, this is very effective, very helpful. My one friend, he left this English and going to this computer science of this university, like Chinese.
Mhm.
This he spent his very good time, and he do his course very fast.
Okay. Go back to normal course.
Okay.
Okay. Just let us start. You know, the time is limited. Okay, so we don't have enough time before the examination, so we have to try our best to go through all the contents of review.
Time is no time to wait.
Okay. Learning objective of this objectives. Objective 2, we learn Ohm's law, but we all learn Ohm's law in our primary school, right?
Yeah.
And the topology of circuits. This one should be the new thing, right?
Yes.
Topology.
Node branch looping.
In this part, we will learn the definition of law, the branch, the loop, and the mesh. And based on this, we will learn the Kirchhoff law. The Kirchhoff law, we have Kirchhoff current law and voltage law, KVL, KCL. And then we will learn the series connections of resistance, and we will learn the parallel resistance, and we will learn the voltage derivation and current derivation. Okay. And in the end of this chapter, we will learn the delta to Y connection and Y to delta connected circuits, and we need to learn the interconversion of them. Okay, we will get two equations. Do we need to remember that?
Which one? Oh, this why does the transformation?
Yeah, transformation.
I think we are going into
We'll try our best
maybe
to remember it.
see.
Okay, now we're going to the section 2.2 Ohm's law, resistivity. Okay, material in general have a characteristic behavior of resisting the flow or resisting the current. Okay, so this physical property is known as resistance, and we have learned it before, and we use R to present it, and the unit is ohm. And here we have this equation. This equation is the definition of R. What does that mean? We can see from this equation, rho is the material resistivity, L is the length, right? That's here, and A is the cross-section area here. That means the value of R is decided by the property of itself. Okay.
These two property are
Yeah. So, what does that mean? So, we have the definition of R. It's decided by the property of itself. But in our calculation, we didn't use this equation, right? Why? The same reason, right? It is hard to get what? A, L, and rho. It's a little bit hard to get them all relative hard. Okay. Because we use Ohm's law, right? Ohm's law is more quick than this one. Okay, rho is material resistivity, right? And the value is from low to high. If the resistivity is low, we say it is a conductor. And if it is high, we say it's insulating. Okay. And if it's not high or not low, it's semiconductor. Okay, we have learned it before, right? So what is the conductor in our life? Conductor.
Individual is conductor.
So conductor, okay. Like this? Okay.
Yeah.
Everything like this material is conductor.
This one.
Yes. Like coffee. It's not called 金属.
金属.
Okay, how to say 金属 in English? It's like cord.
Copper.
Like a cord. How to say that? Like it's a material. How to say that? Cord.
Copper material.
Cord is one type of material.
Copper.
Yeah, copper. And okay,
This is also
like
conductor.
this.
Yes. This is the steel.
Yes.
Aluminium or this is the steel and this is the copper.
Inside
The
is
copper.
Yes, I mean, copper is one type of material.
Yes.
Yes, but I mean, the classification of copper, what it belongs to? 金属. Okay, just let me search. Wait for a minute. Mental? Is it mental? Is it mental?
Metal. Oh, metal.
Metal.
Oh, it is the amount. It is
Is it metal?
metal.
Yes, metal. I mean, metal, sometimes metal is a conductor, right?
Yeah.
And other things, insulator. What is insulator? Other things. Right? Insulator.
Insulator.
Like,
Rubber, paper.
yes, and maybe here the skin of the wire is
Plastic,
insulated.
paper.
Okay, what is a
Semiconductor.
semiconductor? What is
Silicon.
Yeah, good.
Like gallium.
Like
that.
Good. So sometimes we use carbon and this
This is-
silicon is semiconductor. Okay, we say the conductor like metal, they have low resistivity, and the paper and glass, they are insulator, they have high resistivity. And resistors are usually made from metallic alloys. This one, alloys and carbon compounds. It's a compound. Okay, it's a compound, not just a simple material. Okay. Have you ever seen a resistor in your real life? A resistor in our circuit board? Do you see it?
Because when I made it robot, I have a lot of resistors.
Okay.
Can I bring? Can
yes,
I bring?
you can next time. So here, so the most recently we see this one. Okay. Do we see it? Have you ever
Yes,
seen it?
I use it.
Okay.
And this is potentiometer.
So this one is one type of fixed resistor.
Yeah.
The value is not changing with time.
Yeah.
And another one is
Variable
variable resistors.
and potentiometer.
And we can change it.
The
And this
resistance.
one is a coefficient type of variable resistors, and this one as well. So in our life, the most common resistors is this one, the
Yeah.
carbon film type. Okay, now Ohm's law. Old thing, right? Old thing for us. Ohm's law, U equal to IR, and this equation we need to remember it by heart. And here, we need to notice the direction of current and property of the voltage conforms the passive sign convention. Okay, like this way. In this way, we have V equal to IR. But if we change it to the active sign convention, here, I go inside for the negative sign, right? And the V, the equation of V is changed. But we don't like it, right? So we just remember this one. And remember this equation. Okay, so in most of the cases, we have the chance to select the reference direction. Remember, for passive elements, use passive sign convention. For active elements, use the active sign convention. Okay? And you also need to know, you also need to take care about the direction. It is already given. You need to take care of it. Okay? For me, I might change the direction and change it back in an easy way as well. Okay. Okay, limitation, linear of a resistor. What is linear function? You learn mathematics?
Yeah,
You know
linear, non-linear
function?
function. Yes,
So in mathematics definition, we say if a function satisfies the superposition theorem, it is linear. That means if we have f, which is the function of x1 and x2, if it equals to f of x1 plus f of x2, and if f of ax equal to a times fx, if those two equations are satisfied, we say it is a linear function. So look at this example. First order non-homogeneous function y equals to ax. It is linear. Why? It's not a linear. Okay, let me have a look. fx1 plus x2. And it's equal to a x1 plus x2 plus 1. And if we separate them, it's equal to this one. It's not equal to fx1 plus fx2. So it's not linear.
Algebraic.
Okay, so it's not linear. No, but it's linear.
It's not homogeneous because it's not equal.
Okay.
Non-homogeneous but linear, okay, because
It's linear, but not homogeneous.
non-homogeneous.
But why then after this here? But this equation is not satisfied. So it's not linear.
Ma'am,
If we put
for
x1
linear,
plus x2 inside, it must equal to this one.
for
Must
linear,
equal to this one.
for linear condition,
For f
is
x1 plus f x2
to
is
equal
ax1 plus 1 and ax2 plus 2. So it's not equivalent. So it's not satisfied. So it's not linear. Right?
why is this 2? This 2. This side is 1, but how can they get 2? For this 2 is
Ignore this
different.
one. fx1 equal to ax1 plus 1, right?
Hmm.
fx2 equal to ax2 plus 1, right?
Oh,
1 plus 1
Is
is
2.
2. So the right hand side equal to this one, the left hand side equal to this one. It's not equivalent. So it's not linear.
hmm.
Okay. Right. The second example, homogeneous function is a non-linear function.
Yes.
It's obvious, right?
Yes,
It's
because
not equivalent.
2x1, x2 is
Because
x.
on the left hand side we put x1 plus x2 inside and it will become this one.
Yeah.
Right hand side, this one. So
This one is
we don't have
x.
this side. So it's not
Non-linear.
Okay, example 3. Still a homogeneous function, y cosine x is a non-linear function as well.
Yeah.
You can use this first equation to make the solution, right? Okay, so for this one, it's not linear.
This one is not linear because this is 2, this is 1.
Yeah.
So this is not same, but non-homogeneous.
Mm. But not all resistors satisfy Ohm's law. You know this?
Yes.
Because just for linear resistor we have this relation. For non-linear resistor, our R is not a constant. Just ignore this one. Okay. So for linear resistor, it's like straight line, and for non-linear resistor, it maybe have some wave inside. It's not a straight line, so it's non-linear. And if it's non-linear, this one is not satisfied. Okay. The second one, conductance. The definition of conductance. Conductance is another one, is a definition followed by the resistance, right? Our G, we know, is 1 over R, right? So this equation we still need to remember, and the unit is Siemens. G is the reciprocal of R. Just remember this one. And this one is the example. Here we have a electron iron draws 2 ampere at 120 V. Please find the resistance R and conductance G. Okay. So our current I equal to 2 ampere and our voltage V equal to 120. Put it inside the Ohm's law. 100 inside here, 2 inside here.
Yes.
Simply we can get 60
Ohm.
ohm. Our G, we just take the reciprocal of R and we get is equal to 1 over 60 Siemens. Just remember
The Siemens.
the unit. Okay, Siemens.
Oh, otherwise 1 over Ohm. Ohm inverse 1.
Okay, short and open circuit. We see the value of R can range from V to infinity, right? So just look at this one. So this one is 0.0 and this one is infinity. If our value of R is tends to 0, that means this one is a short circuit. Tends to 0 means it's short connected. If the R tends to infinity, that means we open the circuit. No electrons can pass this
Circuit.
circuit.
For this guy answer.
Okay, this one is the derivation of the short circuit and open circuit. Let me just show you quickly. Okay, so for this circuit, we put current source here, and we can see if we put current source here, these 2 points are short connected, right? So we know the current will go through here, okay, and go split here, right? Because inside the circuit box, the R is not to 0. But from this branch, we have R to 0. We know the current always tends to the lower R, right? So the current will go through this way. Okay, do not pass this one. So we say this element is short connected. Okay? And from this one, just open it, is the seizes current and go. This one is a simple circuit, and we use the red wire to short connect this one and this one. And the current, it goes through the I ohm will go through this wire. So the 1 ohm, we say it is short connected. That means if we want to short connect one circuit element in our circuit, we just use a wire, okay, to connect both sides of it, and it will be short connected. So the open circuit, more easy, just cut it. Okay, just cut it. And we can cut this one, and cut this one. Okay. The power dissipation of R. This we will already know. The R, the resistance always dissipate energy. In mathematics, our P is equal to VI. From Ohm's law, we have V to IR. And we put this value inside, and we get this equation. So from this equation, we get another equation of P. That means if we just know the current of our circuit, we can use P to I square times R. And our R is also equals to the reciprocal of G. So we also can write it in the forms of G. Just use 1 over G to instead of R.
We can use this 3, okay? P equal B A square R
Yes,
and B square by
I will
R.
talk it right now. Okay, we can rewrite Ohm's law in this form, right? And put this inside to the V. And we get another one, another form.
Yes.
Our P into V square of R. That means if you just get the voltage of a circuit, and we also can use this equation to get our power. We also can substitute the R with 1 over G. So we get P equal to V square times G. Okay, so in this figure, the mathematical variation is very simple. So in most of the cases, we just remember 1, 2, 3. Okay, and we know this one, and we can erase it very quick in the examination or in our practice. So we just need to remember 1, 2, 3. Okay, this one is the example of Ohm's law. Do you need to
Take it.
talk about this? Okay. Ohm's law question. The parameters is shown as circuit. We need to calculate the current I, the conductance G, and the power P. From this circuit, we give a reference direction. Okay. So the first step. Okay. Here we just follow the steps. Steps is a way to tell us when you get a problem, and we have some steps to solve it. So in the first step, we generally mark the reference direction of current or the reference direction of the voltage. Okay. So in our course, we can see here for the active element, we choose active sign command, right? The current goes inside from the negative sign, right? And here, the resistance, we use passive sign convention, right? Go inside from the positive sign. Okay. Okay. Please stop to playing mobile phone. Okay. Step 2, and we use Ohm's law. For this case, because it is very simple, so we can just use Ohm's law to solve it. And we know our V is equal to 3 and equal to 30. Our R is equal to 5,000 ohm. And we just put V and R inside this one, and we can calculate our I. Our I, after calculation, we get is to 0.006 and here. And you also can write it, use the SI unit, right? Okay, the step 3, we calculate the convexity. Use G equal to I over R, and we get results. And we also can put it back to the MS. Okay.
Millisiemens.
Yep. Step 4, we calculate the power. Here we use the power equation we get before, and we can use this one, and we also can use what? Can use I squared times R, right? Because we already know our R, and we already know our I, right? We know our I. And we also know our V. So I just want to know, why do I use V here? Why I didn't use I? The reason is, the I is the result I calculate. The V is the value it gives us. So, our V must be correct. Our I might be wrong, right?
Yes.
So, if we have some values that is given in the question, we just use it. Okay. We're trying to avoid to use other parameters that we calculated in the calculation. Okay.
But the same result, right?
Yeah, and here we also can use this one and use this one, but we are fine. If we use this equation, it must be right. But if we use this one, if our I is wrong, it's wrong. If I hold V, my I is wrong here, it's wrong again, right?
Yeah. Because this power dependent on time.
Yeah. Okay, here is the short practice. Okay, so you guys can maybe have it fine at home.
You don't? Wait, no, can I do?
Okay, you're gonna have a try here.
Yeah.
Okay, just observe. Inside this one, we have 2 known variables. So in our mathematics, we all learn mathematics, right? This is the general form of function. Okay. Right? In our work, in our class, this one is considered as input. This one is considered as an output. Okay, what does this mean? If we want to get output, we must know the input. Okay, so the same thing. Here we have some known variables. Okay, so all known y must be a function f of known variables. Maybe in this course, what is the known variable? It's I and R, right? What is the unknown thing?
V.
We're trying to get V, right? We're trying to get our R, and we're trying to get our what? P, right? So here, unknown thing, V equals what? I is known.
Yes.
R is known. R equals what? No, G. G equals what?
1 by
1 over G. Okay, all known things equal to a function of known things, right? And also for P. P equal to
R square.
I square R, known known, right? A function of known things will be unknown. Okay. So when we do any practice,
I square or IR square?
I square R.
Here, P.
Okay. I made a mistake here. Thank you very much. I made a typing mistake. I will go back home and correct. Okay. So here we can see, in the perspective of mathematics, if we have three unknown variables, we have three functions to solve it, right? So if we have four unknown things, we need to make four equations, right? Okay. So for this question, we need to list three equations for three unknown variables. And here we see unknown lead to a function of 1, and here and here. So please remember this in your heart. When you're trying to solve a question, you're trying to get an equation. What is the equation for? This equation is for unknown things. And we're trying to make an equation of unknown things based on the known things. Okay, so here, physical perspective. Give some physical quantities and find out other unknowns. And mathematical perspective, give some known variables and solve equations for unknowns. So which one is better for you? Mathematics.
Yes.
Okay. So for me as well, the mathematics idea is more useful, because from this, maybe I need to construct a relation from the physical variable and the notion of mathematics. But if we just go back to the mathematics perspective, it's just a pure mathematics equation. It's quite easy for us, right? Okay, now we're going to see the North branch and the roots. This one is the content about the network topology. It is easy, but sometimes confusing. Because the reason is there are two types of definition. Okay, just let a look at this one. A branch represents a single element, such as a voltage source or a resistor. So for this figure, we have we have 5 elements. Every circuit element is on a branch. Okay. A node is a point of connecting between two or more variables. That means this one,
2, 3. 3 nodes.
yes, this one,
1,
this
B,
one,
C. 3
this
nodes.
one, 3 nodes.
Here. B node, C node. And C node is the reference node, is 0.
A loop is many closed paths
In
in
a
a circuit. This one, this one, this one,
Yes.
this
Yes.
one,
Yes.
this one,
Yes.
this one. Okay,
1, 2, 3, 4, 5, 6, 7, 6.
we should notice if a conducting line connects two nodes, the two nodes is actually a single node like this. Here, two nodes connected by a wire, so it is treated as one node, right? And the second one is a loop. Pass any node only once. So can we like this? No, it just can be passed at only once. Okay, another definition of network topology. For me, this definition is better. Yes, I recommend you guys to use this definition as well. And for this one, for this book, it is the first one. For that book, it's used the second one. Yeah, I know you have that book. It's disappeared. Okay. So in this definition, it is really different, and we can compare. A branch represents a single element, and we have another definition of a branch. This branch is an interconnection of elements passing through the same current. What does that mean? So, in the first case, this one is a branch, right? This one is a branch. But in the second definition, inside this one, just passing one current. So, this one is a branch. So, number of branch is the number of branch is how to say
So,
not small. The opposite of the more.
opposite and more.
Opposite of more. I give
Like
you
less,
more.
meaning
No.
I give you
less.
some more.
less.
Less.
Yeah.
Yes. Okay.
Opposite of more.
The number of switch is less. Okay. Branch is less.
Coming within you need to read a video there.
Okay. A node is a point connecting two or more branches. In the new definition, a node is a connection between three or more branches.
Yeah, some book they
Yeah.
say this node
Yes.
is connected to branches is a
Yeah.
node, but some book
Yes.
say more than two.
Yes. So, I think the right hand side is better.
Yeah. And another book is say, let's see, two or more than.
Yeah, I know. This one is in this book, and another book is this one. This one is better, so I recommend you guys to remember
Three
this
or
one.
more branches, yes.
Yes.
Because
This one, a branch is a connection of elements passing through the same current. And a node is a point connect three or more branches. Because you can see here, this one, the input equal to output. So the equation is no meaning for us, right? Okay, so a loop is the closed path in a circuit. But here, we defined an independent loop. It consists at least one branch, which is not a part of any other independent loop. So this one is more easy for us. So here we have 5 branches, 3 nodes, and 6 loops before, right? If we use this definition. But for this one, we have 4 branches, 2 nodes, and 3
Independent nodes.
loops. We can see the number of branches less, the number of nodes is less as well, and the number of independent loops or loops is reduced as well. Okay. So what is the benefit? We know the essential of circuit analysis is a method to solve equation array, right? So if we use this definition, we'll get less equation. Okay, if you have an equation array with 5 equations and you have another equation array with 10 equations, which one do you prefer? If you need to solve an equation with 5 equations, another equation array with 10 equations, which one do you prefer?
5.
Yes, so if we use this one, you might get 10. If we use this one, it reduces 5. So that is the reason we say this one is better. So I think it is better even for this one. But the reason I talk about this one is the same in this one, in this book. And then to tell you guys the difference between those two definitions and tell you the benefits of another one. Okay, so that's you know which one is better. That is our focus. So what is the time? Okay.
take a look at 10 minutes.
So we still have 15 minutes, okay, and we can finish. And we go for lunch.
We have 15 minutes.
We have 15 minutes. I think it's not good
No.
for us. The reason is,
I have to
You
go
know,
to the last book.
for other courses, we have alarming. When the course is finished, ding. But for this course, nobody told me the course is finished. So I think it is better for me to make alarm by myself, right?
Yes.
If it's 40 minutes, 2 minutes.
Okay. We will finish.
It's time to have a rest. Okay. So do you need to have a rest now?
No,
Or
no.
we just want to finish it and go to
We just finish and go to
go for lunch.
We can finish it at 10.
Okay.
11:30.
So the selection of the independent loop is not unique. But how do we find out independent loops? We say the best way to find the independent loops is the mesh. You know mesh?
Mesh, yes.
Yes. Mesh is the simplest independent loop. But independent loop is not the only way to choose. Okay. We can choose this one, right? We also can choose this one, right? And we also can choose this one. They are all independent. But it's obviously the first one is the most simple one, right? Well, why we still need to know this? Because in some cases, there are something we don't like in the middle of the branch. Because such as dependent source, right? If a dependent source maybe
We can't move out this one.
if a dependent source is maybe
There.
here or here, and it is maybe better to choose this one because
We can move out this dependent source. That's why
yeah.
we
But we can have different choice of independent loops, right?
yes.
Yes. Okay. Next, we're going to see the fundamental theorem of network topology.
Loop less not minus 1.
This
equals
one is more mathematics, so please concentrate on. Okay. A network with B branches. B is
Node.
the first
Yes.
letter of branches, right?
Node.
And nodes. N is first letter of nodes, right? And L for independent loops. L for L. Loops. Okay. We'll satisfy the fundamental theorem of network topology. It is B equal to L plus N minus L.
The branch
Remember?
equals loop plus not minus 1.
This relation is simple.
Yes.
This one is actually the number of the equation we will get. Okay. For topology definition 1, okay, in this book, okay, we have 3 independent loops, so our L equals 3, right? We have 3 nodes, so our N equals 3. So our B, we can calculate it 3 plus 3 minus 1, so we get 5 branches. So match the result to get 4. For topology definition 2, we have 3 independent loops, so our L is 3 as well. So we have 2 essential nodes, and we have B equal to 3 plus 3 minus 1 equal to 5. It's wrong. We should have 3 plus 2 minus 1. So it's 2 equals 4, right? So we have 4 branches for this definition. So why this equation is important? Well, we will talk about the circuit analysis method in the next chapter. So we have 2B method. This one is very basic one. What does this mean? This one means we have 2 times of B equations in our circuit analysis model. That means 2B equations. So for this one, our B is 5, right? So 2B equation means 10 equations. But here, you can see 2B equations use
Four.
8 equations. Okay, so 8 equations is better than 10 equations, right?
Yes.
Okay, so we also have branch current method and other method. Branch
Okay.
current, node voltage, mesh current, and loop current method. Right, and from here we might see, maybe the B equation, right?
Mm.
We might have less equation, maybe have N equation. Do you know? N equation? What type of method we have N equation? N equation is node voltage equation, node voltage method. The node voltage is the variable of this method. Mesh current is the variable of this method, right? So the equation, we can see it from the name. The branch current method means in this equation, in the equation of F, in this equation, okay, we say inside the F is the branch current. Understand? Okay. For loop current, the same. The variable is the loop current. So if we have 3 loops, that means 3 currents. Okay. The equation quantity is related to the quantity of node N, branch B, and independent loop I. Okay. If you know B and N, you know the quantity of equations that you can get. What does that help? If we know the number of equations of each method, for example, this one we have 10, this one we have 8. No, this one has 10, this one has 10, this one has, just for example, this one has 3, this one has 3, and this one has 5, and this one has 3. So we can choose the
3.
method with the less
3.
list equations, which is 3.
You can find
Okay,
easily
so
3 points.
from the topology, we know the N, we know the B, we know the L. And then, oh my mercy, which is the last? And I choose that one. Okay, so that one is the last. And we can decide which method is the best before we start. Okay? Because for one problem, we have many ways to solve it. This one can solve it, this, all the methods can solve it. But we have a best method to save our time. Okay, terms for describing circuit. Here is the tables of the definition of topology. And just go through. Do you know node?
Yes.
Essential node. Just ignore node. So in our book, the node will be essential. Okay.
Yeah.
Do you know bus?
Yeah.
Do you know bridge? Bridge.
Eventually.
So, do you know essential bridge?
Yeah.
So, okay, in our book, our use essential branch as our branch. Loop, independent loop,
Yes. Mesh.
also use independent loop.
Not loop.
And independent loop, we normally choose mesh as independent loop, but not always, most of the case. Okay. So regarding to the case itself, okay. Next, we're going to see the series and parallel. Series and parallel for what? We know series and parallel is two connection relationship. Okay, so here is just describe the connection relation. Here is the element. Here, the block box is not stand for the resistance. Okay, this is resistance for normal circuit element. So we just show the connection relation. Here we can see here inside this line, it goes through the same what? Current, right? Two or more elements are in parallel if they are connected to the same two nodes. this one and this one, and all of the circuit elements are connected between it. Here we can easily find they have the same voltage. So if two elements have the same voltage, we say they are parallel, right?
Yes.
Okay.
For that one.
Please notice the connection of elements can be in series or in parallel. Sometimes we do the conversion to simplify circuits. So look at this example here. Observe the circuit. Observe it. Just let me have a look.
How do I have to find your current?
This one have 5 branches and 3 nodes, right?
Yes.
So the 1 and 2 ohm
Parallel.
is in parallel between node 1 and node 3.
Yes.
And the voltage 10 volts and resistance 4 is in parallel between 2 and 3. Just want to know if the 5 ohm is in parallel with other single elements.
No.
No. Okay.
This 2 is on parallel. We find that this parallel RP, the 5 and RP is series.
Yes.
And then this
okay.
one will.
Okay. So our 5 ohm is in series with 10V and 4 ohm with this part and this part, but not with them individually. Okay. So for simplification, we can write this relation as 5 ohm with the plus to stand for series. Okay. And we use 2 slash to stand for
Parallel.
parallel. Okay, so we can say 5 ohm is in series with 10 volts parallel 4 ohm. And this one we also can read it out, right?
Yes.
So the 5 ohm is in series with 1 ohm and
Parallel
in parallel
with
with 2 ohm.
But
In parallel first.
this is voltage. How can I parallel make this? Can you make this go back this page?
Okay,
This is the voltage.
which one?
You write here 5 ohm plus 10 volt parallel. This
It's
4.
just a relation. Just relation. It's not a mathematical equation, okay?
I understand.
It's not a mathematical equation. Just maybe to show it like a mathematical equation, but not a real mathematical equation. Just show the relation. Here, plus means in series. Here, slash means in parallel. Okay. A diagram of circuit analysis problem. This one is the original current model, and we want to simplify it. Why we want to simplify it? For a circuit with 10, if it has 10 resistors and 6 capacitors and other things, we know connection, right? We might have many nodes, many branches, and many mesh. But if we can simplify it, maybe to 1 resistor and 1 conductor and 1 capacitor, and it will become more simplified. Okay. Do you know admittance?
Admittance here.
Impedance. Yes. So when we learn the impedance and admittance and for any complicated circuit,
This is the imaginary pair.
for any complicated circuit, it can be converted to maybe a simple case like this. It can be converted like this. So for this one, we can see a simple topology, right? But if we have a very large system, and if we can simplify it, we will reduce the number of equations for calculation. So for this perspective, for this objective, we can say the simplification for a circuit is very important. And for us, we are trying to circuit analysis. And now we're trying to learn the skills that can simplify the circuit. Here, and we know we can use series and parallel conversion and white delta conversion and to convert a circuit model to a simple circuit model.
Sometimes we convert to Y to delta, sometimes delta to Y.